everybody. We're going to go ahead and begin. We were waiting for someone to come in to do the introduction, but parking was an issue. So without further ado, we'll just introduce Psarris, and I'll let you know there's going to be questions and answers as well, period with that. So if you could write it down on your own piece of paper or grab one over here and put it in a box, and we'll answer those later. We'll have somebody answer those. So, and is the light good? Spike was thinking of taking the lights all the way down, but if you want to take notes or things, you can't do that for the presentation. Spot, do you want the lights on?
This seems pretty good.
This seems good. Okay, we're going to leave it like this. So, thanks for coming, Spike. Hey, let's get out of this show with you.
Well, thank you for coming tonight. Friday night, not necessarily the easiest night to get away. We have several presentations scheduled here this evening, as I'm sure you're aware. The one that was asked for first is on distant starlight. And for those of you staying for all three talks, there will be a little bit of overlap in a few of the topics. Generally, I don't have the opportunity to give multiple sessions in one evening like we're doing here this evening. So some of the things that are talked about need to be set up in that context. So there will be a little bit of overlap, not a whole lot. And some of the things, if something shows up more than once, that's because it's an important subject that needs to be talked about, so that's fine too. As to why I'm here, I speak, as I have the opportunity, on the creation evolution debate, controversy, and I do so as a former atheist. I was an engineer in the U.S. military space program for a good part of my adult career. I was an atheist and evolutionist until well into my adult years. And I was an atheist because I was an evolutionist. I was a total science nerd from yay high. I could read at age 3, and I was devouring science books. I had a geology textbook from when I was 7, so that's the kind of kid I was. And I rejected God because I understood science showed there was no God. Science showed how we got here without one, so why would you want to believe in one anyway? And it wasn't until working in the space program and the position that I had that I was confronted with evidence against my atheism and evolutionism. And after spending a lot of time trying to disprove it, because I didn't like the implications of it, I eventually had to acknowledge that creation was true. Now what do I do with that information? Well, that means there's a creator to whom I'm accountable, and I didn't want that especially. So I struggled against that for a while, but eventually became a Christian as a result. Now I like to mention this when I talk because I became a creationist first and a Christian afterwards. And a lot of times in the creation-evolution controversy, the evolutionist side likes to portray the creation side as being creationist because we have to be. They say because Christians are committed to the Bible as being true, that then forces them to affirm that creation is true, because that's what the Bible talks about, and that therefore forces them to deny or ignore all this evidence in the world around us about neo-Darwinian processes having produced us over millions of years and so on. That is a mischaracterization of how it actually is. I'm one of many for whom the opposite is true. I became a creationist because of the evidence, and then became a Christian after that. And I know many people in the creation movement who had similar journeys. I mean, everybody's story is a bit different, but it's not that everybody was raised as a Christian and taught to believe a certain way. That's not it at all. One thing that goes on in this whole controversy is the culture has done a really good job of really mischaracterizing and misportraying what the creation movement's about. Perhaps there are people who are denying science. That's not the community that I'm part of. I know a lot of degreed, credentialed scientists, some of whom have very distinguished careers in the sciences, some of whom are atheists until fairly late in life, as I was. I'm not trying to place myself on the same level of some of these people. But again, just to make the point, this is not a matter of faith versus science. I'm here to argue that science is on our side. And by our, I'm talking about the creation side. Perhaps not everybody here holds to that same position, but that's fine. Welcome, if that's the case, or even if it's not the case. Everybody's welcome, right? So, our topic tonight, distant starlight. Does it disprove biblical creation? Oftentimes it is said that you can easily disprove the story of creation in the Bible with, say, 4 words. We see distant stars. That's fairly straightforward. The argument is, or it seems straightforward, the argument is that we see light coming from faraway objects, and of course it doesn't reach Earth instantaneously. It takes some time to get here, depending on how far away the object is, because the speed of light, of course, is not infinite. So this this light beam travels here from out there. It takes a certain amount of time to do so. Well, a lot of these things are really far away. So far away that the light would take millions or even billions of years to get here. So those of us who affirm that creation happened recently would seem to be faced with a problem here. And it's a fairly simple calculation, isn't it? The amount of time necessary for that light to get here is the distance divided by the speed. Now that's a pretty straightforward calculation. So it would seem to prove that there's some real problems for the creation view in the world around us, in the universe around us. For example, the Andromeda Galaxy is about 2.5 million light years away. Now a light year is actually a unit of distance. It's the amount of time that light travels in 1 year. So therefore, light from the Andromeda Galaxy would seem to need 2.5 million years to get here. Well, how can this be if the Earth, and by extension the cosmos, are not actually millions of years old? Looking further out into the universe, we see things that are 13 billion light years away. Billion, that's with a B. A million has 6 zeros, a billion has 9 zeros. So a billion is 1,000 million. So 13,000 million years is how far away some of these things are that we're seeing. And we're seeing stuff further back the more we look. As our technology has gotten better, and as people are taking longer exposure photographs with space telescopes and so on, we're seeing things that are extremely far away. And of course, the non-creationist community, if you will, points to this as being a definitive, fatal even, problem for the creation viewpoint. This is the Rational Wiki, which of course is a popular atheist site, where they had this large discussion about the starlight problem, all the ins and outs of it, and how thoroughly it discredits a recent creation. Even some Christians would say this is a problem for recent creation, and as a result, do not affirm recent creation. For example, Dr. Norman Geisler, who has done very good work, is an excellent scholar, written a number of books, and has been a very effective defender of the truth of Christianity through his career, is not a creationist, though. Here's why. He says, I think the speed of light is the crucial thing. If you can prove that the speed of light changes, you probably convert me to a younger creationist. As the situation is, or so he thinks the situation can't be solved unless you can do something with the speed of light. But short of doing that, he's not a younger creationist. Dr. William Lane Craig, another great defender of the truth of Christianity, very good debater, prolific author, and so on. He's not a younger creationist either. He says the scientific evidence overwhelmingly supports the idea that the Earth is very ancient. When you think that we can see the stars, that very simple fact that you can see these stars billions of light years away shows how ancient the universe is. And there's more quotes like this I could provide. I'm sure you're aware that this is seen to be a really serious problem by a lot of people. This problem, though, is actually not even a matter of billions of light years. What do I mean by that? This is the closest star to us, Proxima Centauri. Light from here, I should say, let me back up a minute. This star is a little over 4 light years away from us. Therefore, according to this way of thinking that we're talking about with this issue, light would need 4 years to get here from there. Now, could Adam see this star when he was first created? Could Adam see any stars? I mean, this is the closest one. So, if light just traveled here as portrayed in this issue that we're talking about, Adam wouldn't be able to see any stars. Not for 4 years, and then they would slowly start blinking on one at a time. That doesn't appear to be what the Bible's talking about. It appears to be implying there that Adam could see stars when he awoke. So this isn't merely an issue of how could we see things that are farther away than 6,000 light years. Basically, any star has this issue surrounding it. And for the rest of my talk tonight, I'm going to call this, just for abbreviation, the LTT issue, standing for light travel time. Here's why this matters. The Bible doesn't tell us specifically when the Earth and universe were created. It doesn't give us a date or anything like that. What it does do is tell us when Adam was created, because it gives us genealogies of various people having children who had children. It gives us all the ages these various people were at the time. And if you add up all the genealogies, you can figure out that even if you wanted to go a little higher than that, but it's still only in the thousands. So Adam was created roughly 6,000 years ago, and then the Bible tells us elsewhere that God created man in his own image. In the image of God created he him, male and female created he them. That's Adam and Eve. And God saw everything that he had made, and behold, it was very good. And this all occurred when? On the sixth day. The sixth day of creation was when Adam was created. Genesis 1 says, in the beginning, God created the heavens and the earth. That appears to have happened just 6 days earlier. So if Adam were created 6,000 years ago, then the universe, or the earth and the universe, quote unquote, the heavens, were only 6 days older than Adam, so they would be roughly 6,000 years old as well. And this is affirmed elsewhere in the Bible. For example, when Jesus was asked about divorce, whether or not it was permissible, some of his detractors said, Moses permitted a man to write a certificate of dismissal and to divorce her. And then Jesus answered his detractors. Jesus said to them, he wrote this commandment for you because of your hard hearts. Now here's the key sentence that I'm getting at. But at the beginning of creation, God made them male and female, referring to Adam and Eve. So Jesus is referring back to Adam and Eve as the pattern by which God intends humanity to live. In other words, Jesus was saying divorce is not part of God's plan. My key point here, when did God make them male and female according to Jesus? Well, at the beginning of creation. Not 13.8 billion years after creation. At the beginning of creation. So the Bible affirms that heavens and earth were created basically at the same time Adam was, just 6 days earlier. That would put the earth at only 6,000 years old. And by extension, the universe at only 6,000 years old, as measured by a clock here on earth. So it would seem then that this problem would disprove the biblical account of creation and confirm the Big Bang model. But there's more to the story than this. The LTT issue is not a straightforward argument as it is usually portrayed, as I've been portraying it. There's actually a lot of assumptions within this argument, as simple and straightforward as it seems. Can you spot these assumptions? Well, let's talk about one of them. For example, our calculation of time equals distance over speed. Let's talk about speed. Dr. Norman Geisler mentioned the speed of light and how that would affect this issue. Well, it should be fairly clear that if the speed were different in the past, then that would affect the amount of time that this calculation would produce, right? So here's an assumption built into this argument. The assumption is that the speed of light has never changed in the past. And in fact, among creation circles, there was once a lot of interest in this idea. There was a proposal that the speed of light used to be a lot faster in the past, and that was reflected by some of the measurements we had of it from history. So again, hopefully you can see if the speed of light used to be a lot faster, then light would need a lot less time to get here, and so that would answer the LTT issue, right? Now, as people have looked into this idea more and more, it hasn't really withstood scrutiny. So although there are still a few people who think this might be a valid option, for the most part, people who were advocating this previously are no longer doing so. I like mentioning it, though, when I talk on this for two reasons. Number one, it's a good illustration of an assumption, right? Because it's fairly clear how that one assumption would change the whole outcome of the calculation. And number two, because quite a few people have heard of this and are wondering if it still could be valid. But this assumption seems to be reasonable. It seems like the speed of light has been constant through history. That being the case, what else is there to talk about with this LTT issue? Turns out there's a lot we can talk about. There's actually 7 assumptions built into the LTT issue as it's been stated. Specifically, ones made by those people using this as a challenge for biblical creation. And for that matter, there's more than 7, but I'm limiting my talk here to just the 7. Here are the assumptions. I'll list them for you, and then we'll talk about each one. Assumption number 1 is typically something that the person stating this problem is assuming. And that is the Big Bang is consistent with the universe, and biblical creation is not. Second assumption is that the Big Bang is consistent with the LTT issue, and biblical creation is not. Turns out the Big Bang model actually has an LTT problem of its own. We'll talk about that. Assumption 3 is that we know light's one-way speed. We talked about sort of about that a moment ago, but there's a different twist to this that we'll cover here also. Assumption 4 is that the speed of light is constant through space. Assumption 5 is that light has always traveled the entire distance from these objects to us. Assumption 6, light always traveled as it does today. Assumption 7 is that the universe has no center of mass. Now, what does that have to do with anything? Well, we'll talk about that. We'll see why that's important. So let's go through these one by one. Assumption 1 is that the Big Bang is consistent with the universe in the first place, and biblical creation is not. This actually is an invalid assumption. Now, normally at this point of the talk, I would spend some time discussing this, but as we have the opportunity this evening for multiple talks, basically my next talk is all about this one assumption. So the next talk is talking in more detail about the Big Bang model, showing that it doesn't actually work. It's not a valid scientific model. It does not properly fit the universe we see. So for this session, we're going to skip this one for now, just acknowledging that it is an assumption built into this challenge as it's usually given. Assumption 2 is that the Big Bang is consistent with LTT, and biblical creation is not. Well, let's talk about this one for a little bit. This is a sky map of the cosmic microwave background, or CMB for short. This is a depiction of the differences in temperature from microwave radiation that, as it turns out, is coming to Earth from all directions out in space. And if you're not familiar with the sky map, here's how they make these things. So here's some animation shows a galaxy, i.e. us in the Milky Way. Now, being within the Milky Way, when we look in various directions, we see lots of stars. So here's the Earth, and if you can imagine everything we see sort of projected onto a sphere that surrounds us, and then you unwrap that sphere, that's where these sky maps come from. So this particular sky map shows temperature variations across the sky of this microwave radiation coming at us from all directions. And it turns out this radiation is almost exactly the same temperature everywhere. This radiation through the entire universe is the same temperature to within 1,000th of a degree. Well, that's very interesting because this actually creates a large LTT problem for the Big Bang. The Big Bang says the cosmos can't be like this. Even with the amount of time that the Big Bang model supposedly provides for people working with this as a model, turns out there actually hasn't been enough time for various parts of the universe to come to the same temperature. As an illustration of this, let's say there's a galaxy, we're looking off in one direction in the universe, and we see something 10 billion light years away. And then we look in the opposite direction, and we see something else 10 billion light years in the other direction. Well, how long would it, so if it took light 10 billion years to get from here to here, how long would it take to get from here over to here? Well, that would be 20 billion years, right? The problem is the universe, according to the Big Bang model, is only supposed to be 13.8 billion years old. There hasn't been enough time for light to travel from this edge of the universe all the way over to that edge of the universe. And what that means is if light can't travel someplace, because there hasn't been enough time to do so, then there can't be any other interaction between those two regions either. In physics, you would call this being causally connected. You can't affect a region that is outside of the distance that light can travel in the time you have available. Because light is the fastest thing that can move. So if light can't even get there in time, then nothing else can get there. Sound waves, for example, or various kinds of radiation like infrared radiation, which is a form of light anyway. So heat can't travel, anything can't travel. If light can't get there, then there can be no connection between the opposite sides of the universe. So the Big Bang model says there hasn't been enough time, quite literally, even with 13.8 billion years to work with, there hasn't been enough time for different parts, for opposite parts of the universe to have reached the same temperature, because they've never interacted thermally. Yet the entire universe is the same temperature. So the Big Bang really has a light travel time problem of its own. The universe appears to have communicated, if you will, across different parts of it, even though there hasn't been enough time to do so, according to the Big Bang model itself. Now, secular cosmologists are, of course, aware of this, and they will tell you it's been solved by something called inflation. So you're going to see this graphic again in the next presentation, but this is a two-dimensional graphic of what the entire goes this way. So in the beginning, there's a quantum fluctuation where the universe popped into existence in the Big Bang, and then it immediately went through a period of inflation, where it blew up, it exploded, grew massively in size at multiple times the speed of light. So right after it popped into existence, it immediately went kaboom and got much bigger. Well, what would cause a universe to do such a thing? To expand faster than the speed of light, many, many times faster than the speed of light, by the way, against gravity. What would cause such a thing? Well, we're told that this is the inflation field that is caused by a particle called the inflaton. But what is an inflaton? Has anybody ever seen an inflaton? No, no one ever has. Is there any room in standard particle physics for this particle called the inflaton? No, there's no place for it that we can tell. Is there any reason to believe in the inflaton other than the fact that the Big Bang model needs it to solve the LTT problem? No, it turns out there's not. So the inflaton is a hypothetical particle, or conversely you could say hypothetical field, which means the same thing. Different two sides of the same coin, basically. A hypothetical particle that's been made up for no other reason than that the Big Bang needs it. Because if this thing didn't exist, then the Big Bang would be disproved, it would be falsified. And since we know, quote unquote, that the Big Bang is true, therefore this particle that can cause universes to inflate faster than the speed of light must be true. But this particle is completely outside of known physics, as I think I've already said. As this author here says, what drove inflation? Well, nobody knows. Physicists have suggested different models to describe the inflated universe, but all the solutions are mathematical conveniences with no particular physical basis. All the theories of inflation amount to proof that we don't have one good theory yet, says this astrophysicist. Now, if you look into inflationary theory, it's become very sophisticated and it's a lot of math, and it all seems very impressive until you realize basically all they're doing is writing equations for what they needed the universe to have done in order to prevent the Big Bang model from being disproven by what we see. So your ability to write equations to do something like that is perhaps a good reflection of your creativity and mathematical ability, but that has no bearing on what the universe actually did or is capable of doing. As this author said, inflation's theoretical underpinnings may be rather tentative. The inflaton, after all, is a hypothetical field whose existence has yet to be demonstrated. Let me reiterate, this thing has never been seen. There's no experimental evidence for it whatsoever, nor is there room for it, as I said, in standard particle physics. Its potential energy curve is posited by researchers, not revealed by observation. The inflaton must somehow start with the top of its energy curve, and etc. Not only is the inflaton outside of known physics, and not only is there no evidence for it, there's accumulating evidence against it. For example, as our measurements of the CMB have improved, as we've been able to take more and more precise measurements of it, we're finding that the CMB has patterns within it that that inflationary theory can't account for. As this author said, and by the way, all my quotes are from secular authors. I was assuming that's obvious, but just in case it wasn't. This author said, the models most favored by their data, combined with early results, suffer from exacerbated forms of initial conditions and multiverse problems. We'll talk a little bit more about that later this evening. And they create a new difficulty that we call the inflationary unlikeliness problem. That is, the favored inflaton potentials, in other words, the things that this hypothetical particle needs, are exponentially unlikely, according to the logic of the inflationary paradigm itself. Skipping ahead a little bit here. The inflationary paradigm is now encountering troubles that it did not have before. When inflation was first proposed in 1980, it seemed like a really good idea because it seemed to solve a lot of problems. But the more the idea has been explored, and the more precise data we've gotten from things like the CMB, inflation doesn't work so well anymore. Interesting here, this comment, by the way, was from three co-authors, one of which, Paul Steinhardt, is actually one of the original authors of inflationary theories. So he's rejecting a theory that he helped create, because he's admitting this idea has become exponentially unlikely according to its own logic. So there's something outside of known physics for which there's no room within physics, something never been seen, that is exponentially unlikely according to its own logic. What do we call such a thing? How about the word miracle? Essentially, the Big Bang's LTT problem can only be solved by invoking this miraculous process of inflation. We'll be talking more about inflation here later on this evening. So our second assumption is that the Big Bang is consistent and does not have an LTT problem of its own, but that's not true. It does have an LTT problem of its own. They will tell you it's been solved, but if you look at the solution, it doesn't withstand scrutiny. Assumption 3, we know light's one-way speed. Well, this seems pretty straightforward. I mean, obviously you need to know the speed before you can make this calculation, right? But the key phrase here, let me back up a minute. Do we know the speed of light? Yes, but we've only ever measured its two-way speed, not its one-way speed. And this calculation is a one-way measurement. It's measuring the time it takes for light to get from there to here. That's a one-way trip. So why is that difference important? Well, it has to do with Einstein's theory of relativity. And let's talk a little about that. This is Hussein, or I'm not quite sure how to pronounce this man's name. Hussein Bolt? Hussein, thank you. Here he is winning the 100-meter dash in the China Olympics in 2008. He set a new record of 9.69 seconds, and he's actually broken his own record since then. Now, this is a pretty precise measurement, 9.69 seconds, down to the 100th of a second. That's pretty precise. How do they measure this time? How do they know how fast he ran the race? Well, they measure when he crosses the finish line here, right? There's sensors, and they've actually gotten really sophisticated, being able to tell the instant part of anybody's body crosses that line. So, when the clock stopped, it said 9.69 seconds. How did they know when to start that clock? Well, the clock had to start when the race began. But the race began not here. It began, down here somewhere, right? 100 meters back that direction. So how did they know to start this clock 100 meters away when the race actually started? Well, in the old days, they would fire a pistol, and then someone had to stand there with a stopwatch and click a little button. But that's obviously very imprecise, and today, when we're measuring hundredths of a second, that's not good enough anymore. So today, when the race actually starts, there's some electronic devices that start the whole thing. They're not even firing an actual pistol anymore. It's actually a recording. They go with loudspeakers. But at the instant that happens, an electrical signal zips down a wire and starts this clock here. Now this all works out fine because even though strictly speaking it's not 100% accurate, if you think about it, the electrical signal takes a little bit of time to get to this clock, right? How fast does the electrical signal travel? At the speed of light. So over 100 meters, that's a brief instant. So that doesn't affect really the accuracy to any practical degree. So why am I talking about this? Imagine, okay, so here we're trying to measure the speed of a human runner. Imagine if you were trying to measure the speed of light. How would that work? Well, the race would begin back here somewhere, and then the light beam would travel very quickly and reach a finish line. But that clock wouldn't have started yet, would it? Because the signal telling the clock to start is traveling also at the speed of light. So the light beam would get there at the same time that the signal arrived to start the clock. So your clock would say 0 seconds, right? So we see there's some practical issues then in measuring something as fast as light's speed. If you're going to have separate clocks where this clock, here's the start of the race back here, and a signal goes to your finishing clock, well, that works with human runners, but it doesn't work with measuring the speed of light. If you're just sending the light down this one-way path, you can't measure it with a setup like this, can you? So you have to do something else. Okay, so let's say we still have our two separate clocks, but we have this device in the middle. Here's what we'll do then. We'll put this thing physically exactly in the middle of the start line and the finish line. And we have lots of time to do this, so we can measure this very, very, very precisely. And then we'll run wires of exactly the same length to the starter and the finishing clock. And what we'll do is, when we press a button, this sends two signals, this way and that way. That means both clocks will start at exactly the same time, right? And remember, we're trying to measure the time that light takes to get from here to here at its one-way speed. What's missing with this setup, though? There's an assumption here. We're assuming that light travels the same direction in both speeds, aren't we? That light travels the same way in that direction, light travels the same speed in this direction as it does in that direction. Now, that seems like a reasonable assumption, except that right now that's what we're trying to prove. So you can't assume that what you're trying to prove. That's circular logic. Okay, so we have to do it a different way then. We can't have the clocks separate. Let's say we get clever and instead we'll do this. We'll put the two clocks in the same place and we'll synchronize them exactly. Then we'll move this one down to the finish line, and then at a pre-chosen time, let's say 2 p.m. or something, both clocks will start. The light beam will get let loose, and this clock will start ticking. That seems like it avoids the assumption about light's one-way speed, right? But there's a problem. Relativity says that a moving clock changes its measurement of time. They're synchronized here, but as soon as you move one of them, they're not synchronized anymore, because time literally flows differently for the one that's moving. So that doesn't work either. This all seems weird and abstract, I know, but the main point is there's no way for us to measure light's speed in only one direction. We can only ever measure it in a round-trip fashion, like this setup. If we have one clock from which we send a light beam out, bounce it off the mirror, and it comes back to the same place, now we can trust our measurement. But this is a two-way speed of light because the light goes in this direction and then the light comes back in that direction. This setup does not tell us the one-way speed of light. It could be equal or it could be unequal. But as long as the inequalities compensate for each other this direction to that direction so that the overall speed never changes, we have no way of knowing. Is this too weird for everybody? Or does this make sense? The reason, so here's a summary of what's going on here. In trying to measure the one-way speed of light, you can't start with your clock separated because you have to signal the one at the finish line, and you can't do that with something going as fast as light. Nor can you start with the clocks together, because moving one of them is going to throw off your synchronization. Ultimately, it's impossible, this is my overall point here, it's impossible even in theory to measure the one-way speed of light. You can only ever measure it two ways, out and back, like bouncing off a mirror or something. So we can only ever measure its two-way speed. Einstein himself said this was an implication of this theory. He said that light requires the same time to traverse one path as for the other path, like in that example I showed you where it was being split. It's neither a supposition nor a hypothesis about the physical nature of light, but a stipulation. What's a stipulation? It's something you can choose for a particular situation, which I can make of my own free will. Einstein said in any physical problem where you're dealing with a one-way speed of light, relativity says you can choose whatever one-way speed of light you want. And it works. And it's allowed by relativity. So, that means that this calculation of LTT, which relies on the one-way speed of light, has a problem, doesn't it? The one-way speed of light is arbitrary. Einstein himself says you can choose whichever one you want, as long as your overall other choices compensate. What do I mean by that? We can treat the universe as if light is reaching here instantaneously. Light has an infinite speed incoming, as long as we also agree that its speed back the other direction is twice the quote-unquote conventional speed of light, so that the total round trip time doesn't change. I've probably lost everybody in this room by this point. Strange stuff, right? But this calculation relies on us knowing the speed of light in only one direction, from there to here. Einstein himself said you can never know that speed. It's, in a sense, it's an improper question, because it's not something you know, it's something you choose for the particular problem you're dealing with. So this whole calculation relies on a one-way speed of light being an absolute thing, when Einstein himself said it's not an absolute thing, it's arbitrary. You just choose whichever value you want for the particular problem you're working on, as long as you compensate for that choice elsewhere in your calculations. So the overall point of this is that the LTT issue is not a valid challenge anyway, because it relies on something being absolute, which relativity says can never be absolute. Now, everything I just shared with you is true, but isn't the easiest thing to understand necessarily. And even people who do get it, think some people think, yeah, that sounds too clever by half. It's like an accounting trick or something. You're just trying to avoid the whole question. Well, actually, no, it's not avoiding the question. It's invalidating the question. The question, as it's posed, is not a valid challenge. Nevertheless, some people aren't satisfied with that, so let's go on and talk about other assumptions still that are built into the LTT problem. For example, there's the idea that the speed of light is constant through space. So again, we're focusing on the speed part of this equation. Now, we've already talked about how the speed of light being constant through time, through history, seems like a reasonable thing. But is it also constant through space? Where have we ever measured the speed of light? We've only ever measured it within our solar system, because that's the only place we've ever been. We have a few spacecraft at the edge of the solar system now, but other than that, everything else is deep within the sun's gravitational field. We've never measured the speed of light out in deep space. Is it different out there? We have no way of knowing. But think about it. If the speed of light were different in deep space, where it's not traveling through the gravitational field of a star, for example, that would change the whole LTT problem, wouldn't it? Because we are in the Milky Way galaxy here. What if, in between stars, light traveled faster? Well, that would reduce the time necessary for it to get here. What about deep space in between galaxies? Light traveling in intergalactic space is far away from any significant gravitational influence. If gravity affects the speed of light, then light would travel much more quickly through deep space, and it would get here in a lot shorter time. Now, I'm not saying that this is the case. I'm merely pointing out, number one, we've never measured it out there because we can't, so it's only an assumption that it's the same, but that's my point. It's an assumption. And number two, there are some people who are investigating this idea. I don't know if this idea will pan out or not. But meanwhile, it remains to point out that this is an assumption built into this calculation that is not necessarily true. This is just an assumption at this point. Assumption 5, that light always traveled the entire distance. Now we're back in this equation, but now we're focusing on the distance aspect of it. This whole calculation assumes the light had to travel all the way from the star, or whatever it is we're looking at, to here, doesn't it? But the Lord had to create things in a mature state, didn't he? Would that include, perhaps, the starlight itself being created on its way to us? Now, most people acknowledge that mature creation is necessary for at least part of what the Lord did. Because, for example, Adam woke up to functional fruit trees. Mature fruit trees, they had fruit on them. He didn't wake up next to a pile of acorns and fruit pits. Nor, for that matter, did he wake up as a baby or an embryo. He woke up as an adult person. So certainly, at least some of the creation was created fully mature and functional. Now, if Adam looked at the fruit tree and said, you know, it would normally take several years for that thing to grow, well, it didn't take that in this particular example, did it? It has taken that since Adam's time, but not at the very beginning. But some people don't like the idea, though, that we extend this scenario out to the distant stars, because they say it makes God deceptive. Why is that? This is a supernova, right here, I should say the remnant of a supernova, that occurred in the year 1987. Thus its name, 1987A. So we saw a star here that then blew up. And this has actually been closely observed during this whole time. And we've learned a lot of really cool stuff about how supernovae develop. This is what it looks like today. But again, this used to look like a star back 30 years ago. However, this thing is 168,000 light years away. Conventional thinking then says this is a light will take 168,000 years to get here. But if the Lord created this light being as is a fully formed thing in between us and out there, what would that look like? Well, there would be this beam of light 168,000 light years long, right? Now, we saw a star there for almost the first 6,000 years of history. So the first 6,000 light years of that beam had a star in it, or portrayed a star, I should say, had the image of a star. Then, 6,000 light years into it, was the image of this explosion. After the image of the explosion came the images that we're seeing now of the spreading gas rings. And then presumably behind it are the images of the gas rings getting even further apart, etc. But the point here is, was there ever a star out there? No. Because the light beam had the image of a star and only part of it, and then the explosion, etc. So, the idea of mature creation, some people are troubled by it because they think it makes the Lord deceitful. That he showed us things in these beams of light that never actually existed, that he never actually created. I don't think that would be deceitful. Again, if Adam woke up next to fruit trees, was he deceived into thinking that they were actually several years old? Well, no, because the Lord told him these were created a few days ago. So I don't personally have the issue with this being deceitful as some people would. I would also point out that you can't restrict the scope of maturity to only the Earth. You have to include stars also, or at least one of them, our sun. Because if Adam could see sunlight when he first woke up, and presumably he could, that means the sunlight that he was witnessing was, in a sense, created in a mature being. Why is that? Because our understanding of stellar physics tells us that when photons are made by nuclear fusion inside of the sun, they take several thousand years to work their way out to the surface. Once they reach the surface finally, they then shoot to us at the speed of light in 8 minutes and 17 seconds, whatever it is. But several thousand years to get there. So if Adam could see sunlight, which he apparently could, that means at least part of this sunlight in the beam and the photons within it had to be created mature as is. So in the case of at least one star, then, the light beam had to be created in transit, so to speak. So we have to account for that in our thinking, at least. So, the assumption that light always travels the entire distance. Some people say, well, mature creation would take care of that. Well, it would take care of that. But, again, some people aren't all that happy with that idea. So let's look at some other assumptions. Assumption 6 is that light always travels as it does today. Back to our calculation, again, we're addressing speed. This idea here is based on passages like this in Genesis 1, where God said, let the earth bring forth grass, herb yielding seed and the fruit tree, etc. And then the earth brought forth grass, and so on. The word brought forth here is the Hebrew word dasha. Now notice, Genesis doesn't say that the Lord said, let there be grass, and poof, there was grass. He commanded, let the earth bring it forth, and then the earth brought it forth. That implies that there was an accelerated process of growth happening in a very short period of time, right? That being the case, could starlight have undergone a similar acceleration? When the Lord's creating the various contents of the heavens, could he have supernaturally accelerated their light on the way here? Well, he certainly could have, and then of course that would do away with the LTT issue, wouldn't it? Now some people scratch their heads over this and say, well, isn't this explicitly miraculous though? Well, yes it is, absolutely. But then again, so is creation, right? Creation is a miracle at the very beginning of it. So part of the process has to be miraculous. We can't seek a naturalistic explanation for everything. Nor, for that matter, is the universe explainable by naturalistic processes either. As we'll see in the next lecture, you have to invoke a supernatural origin of the universe anyway to explain its existence. So having this stage of the process be miraculous too, well, that's not all that inconsistent with everything else then, is it? So that's assumption 6. Now we come to something that perhaps some of you were waiting for, is a more scientific explanation of how all this happened. And that's based on the assumption built into this problem that the universe has no center of mass. Now what does that have to do with anything? Well, the universe having a center of mass or not actually affects this calculation, but this time not the distance or the speed, actually time itself. Why is that? Well, this is all based on the fact that we see redshifts in the cosmos. And I'm going to have more to say about this in the next session. But for now, I'll just note that when we look out into the universe, with the exception of a few things close to us, everything else is redshifted, which is usually interpreted as evidence that these objects are moving away from us. Because when a light source moves away from you, the beam of light that comes towards you is, you can think of it in a sense as being stretched out. It reddens in that process. Conversely, if something were moving toward you and emitting light, the light gets blue shifted. It gets compressed or bunched up in a sense. But when we look out into the universe, we see, with very few exceptions, just a few close by things, but everything else is redshifted. That means everything is moving away from us. And the farther out it is, the faster it's moving away. And this is interpreted among secular cosmologists as evidence that the universe is expanding. That if we are currently in a situation like this, or we're in one of these galaxies looking at the rest, in the future, all the other galaxies are going to be farther from us because they're moving away from us. Well, that means in the past, everything used to be closer together, didn't it? Well, that means, think back far enough into the past, and you reach a point where everything was at the same place, and that's the idea behind the Big Bang model. Okay, so point is, redshifts tell us, or at least I should say, are usually interpreted as evidence for an expanding universe. But we see redshifts in all directions. Everything is moving away from us. Think about that. That leaves us with two possibilities. Number one, we appear to be at the center of an expanding universe because it would look that way from everywhere. Regardless of where you were in the universe, you would see everything else moving away from you. That's one way to interpret this. The second possible interpretation is that we appear to be at the center of an expanding universe because we are at the center of an expanding universe. The observations and the data support either option. But you will not hear both options considered or even discussed. The Big Bang cosmology is based on assumption number one. So of these two options, you have to pick one before you can actually build a cosmological model. Before you can apply any math, you have to decide the answer to this question for reasons I'll mention here shortly. Big Bang cosmologists all go with option number one. That yes, it appears that we're at the center of an expanding universe, but we aren't really, because there is no center to the universe. There can be no center. Therefore, regardless of where you were, it would all look the same way. This goes back to Edwin Hubble. You might recognize the name because the Hubble Space Telescope was named after him. Very important figure in astronomy and cosmology. He was really one of the first people to work out the implications of all this, that there's all these redshifts, and they can indicate an expanding universe, but it looks like we're at the center of the expansion. He said, this is very unwelcome. He said the unwelcome supposition of a favored location must be avoided at all costs. Because if there's a center to the universe, that's a very special place, isn't it? No other place in the universe would be like that place. And if we're at a special place, what would that make us? Special. He said that idea was unwelcome. He continued, a favored position is, of course, intolerable. Therefore, in order to restore homogeneity and to escape the horror of a unique position, the dependency authority must be compensated. There seems to be no other escape. If we see the nebulae, the other things in the cosmos, all receding from our position in space, then every other observer, no matter where he may be located, will see the nebula all receding from this position. However, the assumption is adopted. Notice this is an assumption. There must be no favored location in the universe, no center, no boundary. All must see the universe alike. Is his motivation for rejecting a center scientific? No. It's philosophical, right? He sounds even rather emotional here, doesn't he? This assumption that he kind of pioneered in a sense is that the universe has no center. We're not at the center because the universe has no center, because there can be no center. The universe is without center, without edge, without bound. This is now called the cosmological principle, or sometimes the Copernican principle. And this is the foundation of the Big Bang model. It's built into the math at the very beginning. Actually, you have to choose whether or not the universe has a center before you can do any math anyway. And a lot of Christians who have appealed to the Big Bang as support for Scripture need to be aware of this. The Big Bang mathematically is built on an assumption that's essentially a rejection of the Creator, isn't it? It's essentially an anti-theistic assumption built into the Big Bang from the beginning. But my point for now is, this is not an observation. We don't look at the universe and say it has no center. It's an assumption being made that we don't want there to be a center. Therefore, we're going to construct our mathematics as if it doesn't have one. But it's only an assumption, and apparently a bad one, because the Big Bang model is based on it, has serious problems, as we'll see in the next session. So back to our possibilities. Big Bangers choose this as their foundational principle, that the universe can have no center. But we appear to be at the center of an expanding universe. What if that's how it actually is? What if we go with that assumption instead? Well, that changes the mathematics significantly. If there's a center of the universe, then there can be a center of mass in the universe. That would put us close to the center of mass. And that would cause, at least in the universe's early history, potentially some time dilation. What do I mean by that? Well, one more comment about Einstein's relativity. Relativity says that gravity affects time. Turns out that the deeper you are in a gravitational well, the stronger the gravitational field that you're in, time flows more slowly for you. Now this seems weird because it's outside of our everyday experience, but it's actually been confirmed. In the US we have multiple atomic cesium clocks. So there's one at the Naval Observatory in Maryland down at sea level, and there's one a mile above sea level in Colorado. Turns out those two clocks don't tick at the same rate. I mean, atomic clocks don't actually tick anyway, but, quote unquote tick. The one at sea level measures time a little more slowly than the one a mile above sea level. Why is that? Because of this effect. The one at sea level is a mile deeper into Earth's gravitational well. So time actually flows slightly more slowly there. And it turns out the difference is exactly what Einstein predicted. I'm showing you here the GPS satellites, or one of them rather. I actually got to see the design documents of GPS at one point because I was working with the people on that program. It turns out GPS has to compensate for this. Why is that? Because GPS satellites are in orbit. They're significantly higher outside, well, I should say they're higher within the Earth's gravitational well than we are. We're under a stronger gravity than they are. So time flows more quickly for the GPS satellites than it does for us here on Earth. And since GPS requires very tight calibration of clocks within the system, the engineers who designed this have to compensate for that in the calculation being done here. If it was not being done, then the calibration would slowly drift over time until GPS didn't work anymore. Okay, why am I going through all this? Because of verses like this one, Isaiah 42, thus says the Lord, He that created the heavens and stretched them out. A few years back, the Bible-believing physicist was reading this, and verses like it, and saying, is this poetry? Or did God actually physically stretch out the heavens? If He did, what would that look like? Well, let's say that God created the universe as a small volume of material. It's still unformed and void at this point, but this is what He's about to work with. If that volume were small enough, and that's what the black circle here is, this is the universe that He's creating. If it were small enough, then the amount of material in it would be dense enough to cause a black hole. So the entire universe at this point would be inside of a black hole. And the dotted line here is the event horizon. This is the distance within which the black hole effect is occurring. So this isn't a physical shell. There's nothing here. This is just a distance from the center. This tells you where the black hole ends and normal space begins. Okay, so the Lord starts stretching. As He does so, the volume increases, which means the density decreases, which means the black hole gets weaker, which means the event horizon moves inward. Then He starts forming things within this matter. He continues stretching. Eventually, some of the universe moves out beyond where the black hole is as the event horizon continues to shrink. Now it gets interesting. Now some of the universe is outside the black hole while the rest of it is still inside. And that means time is now flowing normally out here, whereas inside the black hole, it's still almost stopped. Because time inside a black hole flows extremely continues creating, continues stretching, same thing. More and more time is flowing out here, while clocks in here are ticking extremely slowly. God continues stretching. Eventually, the universe is large enough so that the density is low enough so that the black hole collapses and goes away. There is no longer a black hole in the universe. Now, from this point onwards, all clocks in the universe are ticking at the same rate, subject to local variations like being next to a star or a planet or something. But what has happened to this point? You could have millions or billions of years passing out here, while a clock in here only measured 6 normal days. For a while, when the physicist who came up with this, if you ask him how old is the universe, he'll say according to which clock. Because you see these clocks have different time measurements on them, don't they? Which one's correct? They all are. They all accurately measured how much time passed where they were. And since the Bible is very earth-focused in its description of things, the Bible uses an earth clock to describe time. So 6 normal days passed during creation week, while potentially long periods of time passed out here, giving time for galaxies to collide and some other things we see happening out there, and also giving time for light to come in here from out there. It all depends on how the initial mass distribution of the universe was. So, again, another weird concept, and hopefully this one was fairly straightforward as to how this would work. You see, relativity shows time can flow differently in different parts of the universe, depending on how the mass is distributed. So that would give time for light to get from way out there to in here. While still, the universe, by the perspective of the observer on Earth, is how old? 6,000 years. That's what the clock here measured. And that's an accurate measurement as taken from here, which is the time frame that the Bible tends to use. So the assumption built into the LTT issue is that the universe has no center of mass. That's purely a philosophical assumption, ultimately a rejection of us being special in the universe, but it doesn't really match the observations. We appear to be at the center of an expanding universe. And if we are at the center, that opens up some really interesting possibilities as to how time flowed in the past. So the idea that just the starlight disproves biblical creation relies on that list of assumptions we talked about, and more besides those, by the way. Hopefully I've made it clear that although this issue sounds like a straightforward challenge for us, actually it is not. There's multiple possible solutions. And the assumptions it's based on, several are clearly invalid, and several of the others can be challenged. So even as stated, the problem itself is not valid. So I ran a little bit over time because we started a bit late. We are coming back, we're supposed to come back here at 6. Do we want to delay a bit beyond that to give people an hour? I'm seeing heads nod. I don't know if this is a discussion on that or not. Also, it was mentioned earlier, I'll reiterate, if my voice holds up, we'll have a Q&A time at the very end of our time tonight. If you want to write questions down and put them in the box, we will. Are there any other announcements before we break for dinner?
No, well, yeah, one announcement, but there are books over here from the Creation Science Association of British Columbia. So if you want to peruse those, you're welcome to. The Q&A box is over here. And the next session will begin just after 6.
Okay.
Right. Thank you.
6:05 at least.